Jay, I'm making you host for just a second. Just admit the other people if they come in. Yeah,
Yeah, okay.
I'll be back in 2-3 minutes. Okay, Jay, can you make me the host again?
Yeah, I'll just do that.
Let's start. I guess, Jyoti, we can send a message to Supriyo. You can join whenever he's ready.
Yeah.
Yeah, so I hope all of you read through the first few sections in this chapter, which I had sent you a while back now. And I was reading the introductory part again, and I realized, I remember actually that how nicely and succinctly it sort of explains the basic idea. I've been sort of going on and on about this in the first few lectures, but this is a very nice summary of what really one does for majority of circuit analysis in the microwave frequency domain, because of the fact that even though you cannot really analyze them as lumped elements, you can treat them like lumped elements at the terminals. So there is, as long as it's a well-defined point where you can measure voltages and currents, even if it is difficult to measure, but in principle you can define a point where voltages and currents have a meaning. You can then build larger components by treating them as effectively, I wouldn't say exactly lumped element, but the point is that even in a lumped element, the terminal voltages and currents is what matters. And this sort of maps to that. And what happens inside that particular network, of course, depends on the details of what's going on. And there you have to apply either transmission line theory, like you saw earlier in chapter 2, or you have to apply a full Maxwell's equation solution, of course, not by hand, though some cases are, simple cases are treatable by just doing it by hand, but using commercial or self-written code for solving these equations. And then again, using that solution, you can figure out what's happening at the terminal. So it's a very nice introduction, and it sort of goes on to explain where you can and cannot apply, the idea of having a well-defined terminal voltages and currents. So we won't go into the details, but is there any questions about that aspect of, why in some cases, for example, the things they call as the TEM type of transmission lines, and here's sort of a generic example in this figure, which is basically electric and magnetic fields are always perpendicular to each other, and the direction of flow of energy is perpendicular to that particular plane. And this is true for most typical things one uses. And then, in those cases, the definition of voltage and current at a particular point along the transmission line, which is now the one-dimensional direction where you're interested in propagating, has a meaning. And then it also connects to the idea of characteristic impedance. So are there any sort of conceptual questions here at this stage before we move on? Okay, so I'm guessing that a lot of the math, which is fairly straightforward, is familiar to you here because you have studied electromagnetic waves and boundary conditions and standing waves and things like that, and solved Maxwell's equations in those cases. So I was just going to go through some of the points I wanted to highlight in this chapter. And one very important and useful equation is this one. And this is equation 4.8. So these two equations, these are very handy when you're trying to connect lumped element or circuit elements whose terminal properties with transmission lines, and figure out how you would actually write down a circuit equation or a dynamical equation to be able to look at what happens, right? An example, and this is something maybe I will add as a problem in the next homework set, is something we looked at in the beginning. So you have let's say a voltage source, a resistor, and then connect it to an LC oscillator. Right? So we had analyzed this. We also wrote down the differential equation for this circuit. And if this R, let's say, is, well, actually, I should now redraw. So if instead of this circuit, I redraw this in this way, and I think we had briefly discussed this as well, but not in this context. But now if I introduce a transmission line in between, okay, with, I'm already sort of, this is a simple case where the math is not very complicated, where this R is equal to the Z naught of the transmission line, right? Now, we sort of know from our previous discussions is that if I now just consider this part, everything outside of the LC resonator, this is just a transmission line of Z naught connected to a voltage source of the same impedance. So what happens is, in some sense, nothing. Like there's nothing complicated happening in terms of reflections and everything, because this is matched here. So any wave which is launching from the source will not experience any reflection here, and it will transfer, propagate up to this end, and then here it interacts, interacts with this LC resonator, which of course is now an impedance mismatch, and then the wave comes back, and again there's no reflection here, and it goes back here. So there's no multiple reflections, and this is a very typical scenario, idealized somewhat, because I'm saying that because there is no device where you have a perfect match. That this R equal to Z naught is only it's a dream thing. You might have 50 ohms and 50.1 ohms, but it's still a mismatch. In reality, these numbers are actually much worse. Like it's very hard to control these impedances. We'll probably come to this idea of why then it matters for certain kind of circuits. But this is typical in the sense that if one is measuring in an experiment the properties of an LC oscillator in a microwave setup, then there's going to be some instrument, and that instrument is essentially this box, this part here, and then you have some wiring between your instrument and your device, which particularly becomes important if this device is at low temperatures and your measurement system is at room temperature, and there's a long cable, so this transmission line is not very small, and then at the end you have some device. So, but even if everything is at room temperature, you'll typically have some cable, and then there's a question of, okay, how do I figure out the waves which are going to the right and the left in this circuit? Of course, one can use this knowledge that, okay, if R and Z naught are the same, then really nothing is happening. I can just compute the reflection coefficient at this point, and that will basically be the same because there's nothing changing here. But if one was more interested in sort of figuring out not just a steady state problem, but say the time dynamics of how these waves are going to change in time as you first send out a wave and then it encounters this, then you should be able to write down a differential equation of this circuit with some subtleties that there are time delays now between what's going on here and what's going on here. But it's this equation which helps you do that. It's sort of the simplified version of the simple TEM waves which are propagating back and forth. You have a forward going wave, which is usually considered right going are all plus, and then left going are minus. Sometimes it's always the incident wave is plus and the reflected wave is minus. So depending on how you're defining it, that can change a little bit, and one has to be careful about these conventions. We will see that a little bit later when we look at scattering matrices. And then what matters is the voltage and the current at the terminals where the boundary conditions are, right? And I think we had also discussed this earlier. So there is one boundary condition here. So you can then equate for whatever value of z. For simplicity, this was actually z equal to 0. So z is now the dimension, okay, not the impedance. Then then the voltage is just v plus v minus, and the current is I minus. And that then allows you a circuit relationship to say that, okay, there is a current and voltage at this point. I can now equate that to the currents and voltages which I expect to be flowing in this circuit in terms of its dynamic variables. For example, if the charge is Q and the flux in this inductor is phi, then the total current at that point is basically phi over L plus Q dot, right? This is, again, we had written it down. So these are the two conjugate variables you can use to define the dynamics of this. And of course, one can represent one in terms of the other and get rid of one of the two variables completely, which is fine. And the voltage is just either Q over C, right, of the voltage in the capacitor, which is also equal to phi dot, which is the voltage across the inductor. And then similarly, one can do the same thing on this side. And then by equating everything, you will then be able to solve for the what V plus and V minus is. But now you have sort of a differential equation to compute them, and you can even look at the time dynamics. Okay, so this is a very simple but a useful equation to keep in mind for solving these kind of situations. If you're doing just network analysis, it's not that useful, but this is where pretty much everything comes out of. All your quarter wave transformer equations and everything really start from this starting point. Okay. Now, okay, looks like I'm not annotating here, but I'm writing it in this book. It's probably not such a great idea, but anyway, I can fix that later. Okay, so this is something to keep in mind. And this, I guess it's also mentioned here, but one of the interpretations of the, to sort of understand what this characteristic impedance is really telling you is really the ratio of the voltage and current along any point in the transmission line, but not just the voltage, in full voltage, but it's the voltage going right. So it's amplitude of the voltage wave, right? So this is not V over I, where V and I are given by these relationships. It's V plus over I plus, or equivalently V minus over I minus. That is what the characteristic impedance tells you. It tells you the voltage ratio of the voltage wave amplitude and the current wave amplitude at any point along the transmission line. This always has to be obeyed for this to work. And they also talk about here the different kinds of impedances one can define here in this section. So this is again, these are not super useful in terms of doing practical microwave circuits, but it sort of connects the various kind of impedances. If you remember, I had mentioned quite early in the class about the free space impedance being related to mu and epsilon, and this is, of course, is the wave impedance for plane waves. And again, there are all these ideas about it. In general, if it is not a TEM wave, then the mode matters, exactly where you're defining what particular type of thing. They all have different impedances as sort of written here. We are also identified that mu and epsilon also have units of inductance per unit length and capacitance per unit length, which is what we had seen when we did the simple LC transmission line as well. Okay, so these are again useful things to keep in mind. And then, yes, this is another property. I hope you have read this. This now starts to tell you something about the more generic situation. And I want to point out a few things which might look obvious, but at the same time, it might not be so obvious and a little bit subtle. See, in general, when we are dealing with circuits, so forget even microwaves, we know this V is IZ, right? But when we look at it like that, we actually never think about, is this equation written in time domain or is it written in frequency domain? When we learn Ohm's law, this is something which is not really very obvious to us, and it never even comes up, right? And one of the reasons for that is when we are first introduced to Ohm's law, we are actually only talking about one of the two possible scenarios. One is that we are only talking about DC currents and DC voltages. Okay, so in that sense, this is more explicitly omega equal to 0 equal to So in this case, there is really nothing to more to say, because we are talking about things all at DC. We measure a DC voltage, you put a DC current, there's a constant called Z which connects these two, and there is really no problem. The other situation is when Z is frequency independent, in the sense that it's a constant independent of frequency. In that case, it's just a proportionality constant for V and T. So it really doesn't matter whether we are saying that V of P is equal to Z into I of P, because Z is a constant, or we are saying, or we are saying that V of omega is equal to Z into I of omega. It doesn't really make a difference if you don't even explicitly specify this. Okay. Why this? Well, if you have, say, a resistor and you have a time-varying current flowing through it, then it will have a time-varying voltage given exactly by this equation. So this equation is correct, right? I mean, we do this all the time. Now, if you are specifically talking about AC circuits, then you might have to now talk about, okay, well, the frequencies are all independent in a linear circuit. There is no inter-frequency conversion or mixing going on. Then this makes sense that, okay, I have a certain frequency, current at a certain frequency, then the voltage at that frequency is going to be given by just I omega into Z. So that is also okay. Yeah. But if you have a most general case, which is what we are dealing with here specifically, it's actually this which is the fundamental relationship. For a linear circuit, which is what we are mostly dealing with, the current, impedance, and the voltage, we are actually talking about the Fourier component of that. And if there's only one frequency in the problem, then of course it simplifies to that particular frequency. You can drop the omega, but otherwise this is has to be specified very correctly. It might seem like I'm making too much of a point here, but it's not so obvious till you start thinking about it more carefully. Especially when you look at this equation and you're like, wait a second. Now I'm talking about Fourier transforms, and the when you connect this, then it becomes a question of, okay, how do I compute v of t in general, right? Given these current of omega and z of omega, it's not just a simple multiplication anymore, right? So you have Fourier transforms involved, and V is a product of two quantities whose Fourier transforms of two quantities. So that means V of t, this is not equal to some Z of t, I of t. Anyway, the Z of t really has no meaning, but in the context of an inverse transform of Z of omega, one can define a quantity like that. But then this, of course, is going to be related to convolutions and things like that. Because why? Because now we are talking about a generic function of time which can have many frequency components. And hence one has to combine all the different things which are going on, which might be going on in either your current or your impedance, which is now a function of frequency. It's not constant. Okay. So just to maybe pause here, I hope these are all very familiar ideas from other parts of physics courses, right? If there is any doubt here, maybe it's just to ask at this stage. This should all have been covered in mathematical physics or some other courses on electromagnetism and things like that. Um, you do know that if one takes the inverse Fourier transform of this equation to go from V of omega to V of t, then this is going to become a convolution of the zt and I of t.
Yeah, yes.
Yeah. Okay. Just hold on a second. The other reason for emphasizing this point is that coming from an alternate angle, this equation looks a lot more obvious when you're working with microwave frequencies, because you are almost always talking about any property in the frequency domain and not in the time domain. So then it makes a lot more sense that, okay, if I'm talking about a voltage at a particular frequency, then it must be the current and the impedance at that particular frequency which matters, which seems to go back to the basic Ohm's law, which has exactly the same form and we have been using, but without really thinking about it, that it's talking actually about frequency spaces, but except that it's zero frequency. So the more fundamental Ohm's law holds true as sort of the more core equation, provided you are considering them for separate frequencies separately. Okay, so okay, now I'm getting a little worried. Maybe I should close this and hopefully. Okay, I think this is basically the great Apple thing. Everything happens automatically. I probably have spoiled this file copy. Anyway, it's fine. Just been finding that some of the sort of conventions in the iPad and are just so insane. It's like I was trying to copy one file from Google Drive, and it just took me like an hour to do it because it just doesn't work. Um, wherever we- Oh, okay, it did get rid of it. Excellent. Oh, no, it did not. Okay. Um,
I
right?
think you can erase it. I mean, I don't think it's a.
Yeah, I'm sure there's a way. I mean, here somewhere there must be an eraser tool here, right? Yeah, yeah. It'll work. It's fine. I'm just getting cranky and old. Uh, yeah. So then this section, talks about another important aspect, um, which is kind of connected to another thing you have learned in physics in a different context, which is the Kramers-Kronig relationship. You remember that this all of you are familiar with this expression, this Kramers-Kronig relationship?
Yes.
Yeah.
Yes.
Yes.
So it comes in the concept of the dielectric function and what its frequency dependence should be. It's sort of connected with that idea that for physical scenarios, it has to obey a certain set of properties, and that's what is written here because of the fact that this voltage signal as a function of time has to be a real quantity. So then that requires that your voltage Fourier transform has this kind of property, and the current has to have something similar. So that then puts a constraint that your Z has to have a particular sort of frequency symmetry between what we call as positive frequencies and negative frequencies. And similarly for the reflection coefficient from there. So it comes down to the situation that essentially you cannot construct some arbitrary functions of z of omega uh, from quantities which you have access to. It's essentially put restrictions on that, and this sometimes has implications on when you're trying to do some impedance matching over a large range of frequencies. You might see that, oh, there is a solution, but then that solution is unphysical. Okay, so it's sort of important to keep this in mind as well, that your r of omega is always even in omega and x of omega is always odd in omega. Um, so that's basically what I wanted to go through, and we will now look at basically now the network theory, starting with impedance matrices and then going on to scattering matrices in tomorrow's lecture. So I'm hoping you have read this. The generic idea is what I had said in words earlier is written here. You could have some arbitrary multi-port object. This section also makes it even more general that if you don't have TEM modes, then you can define a port for each of the modes separately, but let's not go into that. Let's just say some simple well-behaved but multi-port things, and then you're only interested in these terminals, which they define there, which for example could have been that z equal to 0 point we had done for that example with the LC oscillator and the transmission line, right? And once you define that, then there are well-defined quantities, which is basically now the incident wave and the reflected wave. So if you now look at the convention, so I was telling you that right going is plus and left going minus. That's actually not the strictest of definition. What the correct definition is that plus is the direction of going into the network, okay, and then minus is the direction of leaving the network. That's the convention. You have to keep this in mind very carefully when you're stacking networks, because if you have, let's say, one network here, and it has, this is say port 1 and this is port 2, and this now has a V2 plus going this way. No, actually V2 plus is this way, and then V2 minus is that way. And if that is connecting to some other device, which will have the plus and the minuses sort of in the reverse direction. So it's important to keep this in mind when you are stacking this thing up. So that is the convention. the signal going towards the network is plus, and the signal going away from the network, which is the reflected wave, is minus. So that makes sense. If you say incident and reflected, it sort of makes sense with this particular convention. And you can have these incident and reflected waves as the quantities, but you can also have just the total voltage and the total current as the quantities at that particular point, and that is just by using that same expression I had shown you right at the beginning, right? So you put the Z equal to some value and you get some numbers. So the first concept of an impedance or an admittance matrix is related to these, not the wave amplitudes, which is what is going to come later on, and that is the connection with scattering matrix, but it is related to the total voltage at that particular point. And as we discussed earlier, and it's discussed in this section, it's a unique number, well-defined number. It's not something arbitrary depending on how you decide to choose this. And it later on the book also says that this quantity might not be so easy to measure in a realistic scenario at microwave frequencies for the same reason, but at least there is a well-defined quantity at a particular point. We almost always measure these quantities, the incident and the reflected waves. But this is also useful for analyzing the circuits. And then you just have, now for an N-port network, you have N voltages and N currents. And the Z, or the impedance matrix, is just a straightforward definition which connects these two. And it's obvious that we don't know what's going on here inside. So in general, the voltage at a particular point could depend on the currents at all the other ports, right? That's what the network is doing. It's sort of connecting all of these different terminals. And essentially, that's what this equation tells you, that V1 depends on the current at port 1 with the coefficient Z11. It depends on the current at port 2 with the coefficient Z12. So the first coefficient here refers to the port you are considering, the voltage with the port at which you're considering, and then the second one is basically cycles through the current indices of all the other port. So then similarly, you have one for V2, V3, V4, and so on and so forth. So you have basically now an N cross N matrix. Of course, in general, Z could be a complex number depending on what is inside. So you really have 2n squared numbers, because there's real and imaginary for each of the quantities. But as discussed later in these sections, depending on certain symmetries, certain typical scenarios, the number of independent parameters to represent that network could fall down dramatically depending on certain conditions, and we'll come to that in a little bit later. Okay, so this I hope this is straightforward. This is an extension of the Ohm's law for a single port to that of a multi-port network, right? So I'm now sort of using this single bar and double bar to show that this is now a vector and that's now a matrix, to differentiate between the single component current and voltage relationship from Ohm's law to this more generic quantity. Okay, this is clear? No, it's pretty straightforward. Okay, and then of course you can also define the sort of reverse of it, define the currents in terms of the voltages. This makes sense. Now you have an admittance matrix Y, which is defined just as 1 over Z, and it turns out that it's actually the inverse of the matrix. So again, remember that Y is 1 over Z for a single object, but the Y matrix is the Z matrix inverse. Okay, so inverse in the sense of the matrix inverse, and not in sense of saying that this just becomes 1 over Z11. That's not correct. It's really a true matrix inverse. Okay, and then the sort of the last important thing to know is, how does one actually measure this these impedance matrix quantities, like how are they even there? It's not obvious from this relationship how it is related to the various components in that network. Now, you might have access to the internal structure of the network, or you might have only access to the terminals, and you need a mechanism to calculate or measure these quantities. And this is what it tells you, that the component Zij is the voltage measured at I with divided by the current at Ij with the currents of all the other ports set to 0. Okay, that's what this means. Okay. So if you're looking at a particular terminal, let's say here, or let's say V1, this one, and you're interested in the Z11, then you can only apply a current I in this port. So I is not equal to 0 for this port, and then you measure the V, but you don't send any currents in the other ports. And how does one ensure that there are no currents flowing in the other ports? Remember that we are now talking about the current at this interface point, the terminal, right? So you have some two terminals there. If you don't want any current to flow through this, you just have to disconnect the two terminals, the two ports, which means that it's left open. There shouldn't be any termination in there. This again might seem slightly strange, because you say, well, it's just a port, I have not connected anything, so it is almost always open. But that's the point. You can connect something, and sometimes you need to connect some objects to get the right boundary condition to be able to measure quantities. So for this particular case, you just leave all of them open. That sets all the currents to 0 on the other. So it's kind of natural to see, right? Because you're interested in this quantity, and this is Z11 into I1, Z12 into I2. So if you set I2, I3, I4, all of them equal to 0, then the only thing which will contribute to V1 will be Z11. And likewise for any other combination. So it's just, very straightforward thing, but practically that's how you would do it. Again, if you actually knew what the network was, in the sense that you have a circuit representing that network, then you can use the same idea to compute the actual quantity. And that's what we will do. We will go through some one of the examples which is given here, and then actually understand the properties of such two-port networks in terms of this impedance matrix, and why the value is the way you actually calculate or measure it. Okay. So that's the definition of the impedance matrix and the corresponding admittance matrix. And then
so in these, sorry, yes.
Go ahead.
So when you talk about these measurements, we're talking about the value of V and I at that port. So in that case, we'll need to know both the V plus and V minus, and correspondingly the I plus and I minus, right? We'll need to measure both of those quantities to determine this V in this case.
So, okay, that's a good question. The precise reason why after this we will move to the scattering matrix is because of the fact that the voltages and the currents, even if they're well defined at a particular terminal, at a port, are not so easy to measure at microwave frequencies. So invariably, this is an exercise one never really does, that you're trying to find out the impedance matrix by using this procedure. Yet it's useful to consider this because it has a meaning in terms of how you have defined the network and how the currents and voltages at each particular point are connected. Later on, you will see that from the scattering matrix, you can actually compute everything you need to know. Okay, and again from the Z matrix also you can go to the other things. The precise mechanism of how that voltage is being measured is currently sort of left up in the air. We are not talking about measuring V plus and V minus and then computing the V to in fact extract the Z matrix. And the example we are going to look at is actually going to be of a very simple case where we can actually calculate this without having to do any such measurements because it's a very simple network, but it sort of serves to illustrate the concept and why the impedance matrix is a useful quantity, because it allows you to construct an equivalent circuit in terms of components. And what is the property we know about? So remember, what you have access to, you have only a resistor, a capacitor, and an inductor to work with, right? For linear circuits, this is essentially the three objects you have. And if you're constructing some complicated circuit, which we are now calling a network, which again could be just a piece of transmission line where there's an array of L's and C's, or something else, as we will see in just a little bit. The thing we actually know about these circuits are the Ohm's law for them, for each one of them. So the impedance is something we know. I know how to write down the impedance of L, right? That is just omega L. Similarly, I know how to write down the impedance of C. So the concept of impedance or admittance matrix is useful for building the models. In a realistic circuit, this is something you will never do because it's not possible to do that at high frequencies to measure it. But once you have the scattering matrix, which is related to the V plus and the V minus, then you can go back. Once you know the full scattering matrix of the network, you can go back and construct this as well. Okay, this is sort of an intermediary, more for understanding rather than a practical quantity. Okay, is that clear, Jay?
Yeah, makes sense. Yeah.
Yeah.
So
Yeah, go ahead.
in the multi-port diagram, so a particular terminal or port, there are two lines. So
you mean
you are defining one for the wave going in, other for going out. But in practice, are they two different pin or they are the?
Oh, you are saying that this incoming wave is connected to this line, and this outgoing wave is connected to that. Seems to be written. I don't think that's what they meant to do. It's not that this is some incoming line and this is an outgoing line, but the two together are representing sort of the two terminals of that port. It's just that in the drawing they have, the incident and the outgoing wave have been drawn next to each other. There is no, a transmission line always has two terminals, right? So these two wires here are representing those two terminals, it's not two separate wires for one for going in and one for going out. It's really just a very generic.
Okay, so it is the same.
Yeah, the incoming and the outgoing waves have to go on the same port, right?
Mm-hmm.
Yeah.
Yeah.
The port is defined as a two-terminal case here because the port has always two terminals. There has to be a plus and a minus is what I mean, or a ground and something. So this is just misleading that it looks, they have drawn it like that. Yeah, Sujita?
So we were measuring this Zn or Yn in the circuits.
And the network is really bad today. Sujita, I'm not able to hear you.
But you said that these are difficult to measure. Then are these not the, the Z11 and stuff that we are seeing here?
I think your internet is very unstable.
I can't hear you. Yeah.
Okay. Yeah, Sujita, your network is very bad. But I think I've understood what you are saying. You're basically saying that how is this related to this quantity Z in and Y in we have been measuring in microwave office, right? Is that the question? Okay. Jay, can you say something?
Oh. Sorry.
Yes, it's not shared right now.
Uh, right. Okay. Yeah. So um, that point I was making about the networks actually simplifying in terms of the number of independent parameters, it's related to these special types of networks. Reciprocal networks means that it doesn't matter if you interchange the two ports, the properties remain the same, which means things like Z21 being equal to Z12 like that. So you can look at this derivations here, which sort of work through and show you that what must be the case for the different matrix elements when you have a reciprocal network, and then when you have a lossless network, and the result which comes out from the lossless network is actually fairly obvious, that all the circuit elements and hence all the impedance matrix elements have to be imaginary, right? Because the moment you have a real impedance, then there's going to be dissipation and energy is going to be lost. So a lossless network means that something where the network itself does not absorb any energy. So if there is an incoming signal on one port and there's an outgoing signal on, say, all the other ports in general, then the total outgoing power has to be equal to the total ingoing power. In fact, this is exactly the kind of networks, even though simpler ones like one port version of that is what we have been studying so far, like the LC circuit. And that's why both L and C, only when L and C are purely imaginary, you have that case. But when you have a more generic multi-port network, it can only be composed of imaginary impedances or reactances if you have to be lossless. In some sense, it's obvious, but it's more rigorously shown here. And these properties are actually useful because later on we will be looking at some microwave components, and then the network becomes very simplified once you realize that okay, you actually only need a few few elements, matrix elements, to define them, because they are lossless and they are reciprocal, so we can ignore all of the other ones and don't have to worry about that. Okay, so the example I was going to do is actually this one. It's trivially simple if you have read it, but I will talk about some practicalities here. This is a very generic way of defining a two-port network. It's called a T network because it looks like, shape T. You have two impedances here and then one impedance to ground to parallel. So again, these are the two terminals of the ports, port 1 and port 2. And there is a second version of that, which is sort of is the dual, which is called the pi network, which looks like this. Okay, maybe this is something you can try at home. What this is a minimalistic model for defining any two-port network. Like any two-port network with any properties can be defined by just these three elements, with Z, of course, in general could be a complex and a function of even omega, right? That's how you will get it. So this is sort of a minimalistic model for constructing, it's in some sense, it is sort of the equivalent of the Thevenin and Norton equivalents you have studied for circuits. It's basically something similar to that. Okay. So here in this example, they work out what Z11, Z12, 21, and 22 are for a specific circuit like this, so that you can see, because in this network now you are seeing the different impedances, right? These, that the ZA is an impedance, ZB is an impedance, and ZC an impedances, but this matrix, the elements of the matrix is actually not, it's not like a direct connection to a physical impedance. So this connection becomes a lot more apparent here, that how are they related, right? So to compute Z11, we have to compute the ratio V1 over I1 with all the other currents to 0. So in this case, only one other port. So I2 equal to 0, which means this port is open. So then it's obvious that if you're measuring V1 over I1 here, it's just the impedance across these 2 points. And then it's obvious that since there is no current here, this ZB essentially sort of doesn't play a picture. And then you just have ZA and ZC in series, which is why Z11 is just that, right? Similarly, if you now do it from the other side, Z22 will just be ZB plus ZC, which is what is here. And then the slightly subtle one is V1 over I2, right? With I1 being 0. So this is a little strange because you have to set the current here 0, which means that this is open, and it's the voltage of this guy and the current on that side. And then if you do the calculation, you get that that number is equal to ZC, right? So it's not necessary that each impedance matrix element will be uniquely connected to an impedance in that network. Okay, it doesn't work like that. For this case, Z12 is just given by one of the impedances in this element, but Z11 and Z22 are related to a sum of 2 impedances. So this is again something to keep in mind. It's not always going to be, it's not a one-to-one mapping like this. Okay. So this now connects the idea of a T network to the difference matrix elements, and because it's a reciprocal network, the Z12 and Z21 will be the same. Okay. Now, one thing to note, at least from the way the circuit looks here, looks like here. You might be tempted to say that, well, ZA and ZB are in general different. You know, it doesn't. We haven't said anything about ZA and ZB being the same or different. Yet, Z21 and Z12 is the same. Now, it's a different idea that Z12 doesn't depend on ZA and ZB, which is why it is the same. But the fact that this network is reciprocal actually does not have anything to with this network being symmetric, in the sense that it looks symmetric about this axis, right? I mean, you might have thought that, oh, it doesn't look the same from both sides, so then maybe it is not reciprocal because it doesn't have the same properties when looked at from other side. That's actually a slightly different quantity you are thinking about it. So I thought I'll just emphasize this, that the network is still reciprocal, but it need not have the situation where ZA and ZB are the same. Now, the particular circuit we are going to look into a little bit more detail, and now I'll move to microwave office. I'm going to stop sharing this now. Move to and we are going to do even more simpler version, because this is actually a very common component which we'll be using, and we've already discussed this, actually not in this class, but in my other general lectures about the different things we use for qubit measurements. We are not even talking about impedances now, we are only talking about resistances. Okay, so the frequency dependence goes away, because the resistor, this, you know, as we understand in this circuit, is a frequency independent quantity. And I'm going to make a T network out of this. And not only that, I'm going to make it symmetric as well. So R1 are these two resistors which are on either side of the T network, and R2 is the one which is going to ground. So I can connect the ports, and this kind of a network is actually used for, and this is with resistors. So obviously this is not a lossless network. It's actually used as to build attenuators. Okay. Now, if you look at the circuit, let's say let's call port 1 the input and port 2 the output, though it should not matter. The situation is not only reciprocal, it's also perfectly symmetric now. Can't really distinguish between which one is port 1 and which one is port 2. It makes sense that this will function like an attenuator, because this looks like a voltage divider circuit, right? There is a voltage source, there is a resistor, a second resistor to ground. So there's a current and there's a voltage drop across it. And now this terminal is picking up the voltage across the resistor here. So that means whatever the total voltage was here, the voltage picked up on this side is going to be smaller. So this is of course a DC notion of a voltage divider. But that is the idea, right? You're trying to reduce the voltage or reduce the power going on the other side. So this sort of works. And you can then say simple things you already know about voltage dividers, that the smaller the R2 is in relation to R1, the smaller the voltage here will be. That means the larger the attenuation would be as well. And that gives you a sense of how to sort of think about how this is going to operate. Okay, so again, the Z matrices of this are going to be pretty straightforward, right? So Z Z11 is going to be just R1 plus R2. Okay, and this is now also going to be equal to Z22, because this is R1 on both sides, and then Z12 is going to be equal to Z21, and it's going to be equal to R2. Wow, network is super slow. I don't know if it's just the zoom. Okay, I'm just rewriting the same thing we just looked at in the book for a while. Now, the thing we need to consider is how does one choose the value of R1 and R2? Now, there are really just only two resistors to be chosen to get a certain attenuation. But since this is a component which is being used as an attenuator in a 50 ohm system, we also need some other properties to be satisfied. Okay. Now, of course, I can choose any arbitrary value of R1 and R2, and it will give me some attenuation. But is that good enough? So, Srijita, what property, in terms of the fact that we want to use this as an attenuator, whose job is defined as something which attenuates the outgoing amplitude by some factor, but what else is needed for this to be a good device?
Needs to be matched at either end.
Yes. Match to?
The ports here, port 1 and port 2, it has to be matched to both of them.
Right. So port 1 and port 2, of course, are both 50 ohms. So matched basically
50
means
ohms.
is that if I have made a circuit like this with this attenuator and 50 ohm ports connected on both ends, what it means is that at this plane, gamma has to be 0.
Yes.
Right? That's what matched means. That you cannot have any reflection
Yes.
here. Similarly, at this plane, so this reflection coefficient has to be 0. Similarly, this reflection coefficient has to be 0. Now, because this circuit is completely symmetric, if you ensure one, the other one is by definition going to be fine. And then there has to be some transmission coefficient, which we can call T, which has to have a certain value, which basically is the attenuation factor. Right? Now, one can actually,
Yes.
so this is where the notion of Z11 and Z in will come in, and we'll come that in a little bit. But how can I write down this condition gamma equal to 0 in terms of these circuit elements? Remember that this is an extremely simplified case where it's a resistor and frequency independent. So I don't have to write down any complicated thing. Gamma equal to 0 for a 50 ohm port already means that the effective, so this is port 1, and this whole thing can be replaced by some Z load, right? And gamma equal to 0 implies that Z load is equal to Z0, which in this case means 50 ohms. Okay, so gives a very easy condition to write down. Okay, but how does one compute Z load? Jay, from this circuit, how do I write down the expression for ZL?
You mean from the impedance
You have the circuit in front of you. It's composed of resistors.
that port 1 experiences?
Yeah, that's what I wrote down, right? So if the reflection coefficient at port 1 has to be 0, then the impedance it is seeing at that point has to be equal to 50 ohms. And remember, and I added these points that there is no frequency dependence here, and these are all frequency independent quantities, so you can directly compute that. But what is the expression for ZL? How will I compute it from this?
So we know how to add these resistances, so we can just.
Yeah, so can you write it down? I mean, you don't have to compute the full exact thing, but what exactly will we do?
Like R1 plus the inverse of 1 by R2 plus 1 by R1 plus 50, something like that.
Can you redraw the circuit? I don't know if are you able to annotate it on the screen? Are you on an iPad or some touch compatible thing, or?
Yeah,
So,
I'm on an iPad. So okay.
So maybe you can scribble in this corner, bottom right corner.
I have. Is it happening? Oh, it's not detecting my pencil for some reason. It's only detecting my finger. 1 second.
Ah.
Oh, I think my pencil is out of charge.
Okay, all right, no problem. But what can you just explain by hand, or even maybe just draw by hand your or maybe just tell me the expression so you can use for something in parallel with something, you can just say R parallel with X or something like that, and then
Yeah, so this R2 will be in parallel with R1 plus 50 ohms, and all that will be in series with R1.
exactly. So the important point, which I mean, the rest is obvious. The important point to realize is that there is a 50 ohm here, which is representing the port. Okay, and this is extremely important when one is computing the effective ZL here, right? So why is this, again, I'm emphasizing here, is because when we were computing the elements of the Z matrix, we had talked about keeping that port open, right? That port, keeping that port open would actually correspond to not being able to see this particular 50 ohm. Okay, now this is something slightly important to remember in the context of microwave office and just general in networks. The port we have been discussing for the network so far is not this port. Okay, it's the point to which this port connects. So it's basically like these terminals, right? And this port is from, in micro office where you're connecting to that particular network. So it's just, two connections of 2 points coming here. This port is equivalent to a 50 ohm resistor to ground, and there could be a voltage source here. So one has to be careful about this, that if this port is connected in microwave office, it could have slightly different effects when you're doing measurement of certain quantity, as opposed to when you don't want any current to be flowing this, you might have to disconnect this connection here. It doesn't mean that the port goes away, unless of course if you're measuring cross things, then you cannot really do that. Right? So the network's port is the connection at that terminal, and then this port is sort of thing you're actually using to probe that particular connection. Okay, this could be considered an obvious point, but it's sort of a subtle point to remember. But it's extremely important to know that the requirement of gamma equal to 0 is under the condition that the other side of the attenuator is also connected to a 50 ohm system. Okay, this is again a subtle point you have to keep in mind when you are analyzing circuits. Like when would you say that the circuit is working properly? Because you can actually make a mistake here, right? You buy this attenuator and you say, hey, let me check if it is giving me a small gamma, because you will never get gamma equal to 0. And if you just connect the attenuators, this port, to the port 1 to the network analyzer, which is the instrument which is used to measure reflection coefficient, and you forget the other port. And by forget, I mean either you have not connected it to the second port of the network analyzer, which is a 50 ohm system, or you have specifically put a 50 ohm termination on it to make sure that the full circuit is complete. Okay, the attenuator's value R1 and R2 are chosen to give you 0 reflection coefficient only on one of the ports, only when the other port is terminated with 50 ohms. Okay, I hope this is clear. This is very important when you're analyzing circuits, networks like this, that whether the other end has to be terminated or not, depending on what you're doing. Okay, so the moment you write this down, that gives you one condition for, basically will give you one relationship between R1 and R2, and the other relationship will be related to the transmission coefficient, which is basically tells you how much attenuation you want. Okay, so okay, I think right now I've shared only the microwave office screen. So let me stop and share the full screen. Where did that go? Screen. I want to show you, this is just a calculator which I found online, which allows you to compute what these R1 and R2s should be for a certain attenuator value. Okay, so let's start with something simple, a 3 dB attenuator, which gives a power division of factor of 2. Okay, so it gives you R1 is 8.5 ohms, 54 ohms, and R2 is 141.94 ohms. Remember that the value of Z0 is specified because these attenuation values and the reflection coefficient being 0, they're all very specific to the characteristic impedance of the system you're working in. Sorry, hold on one second. My VPN seems to have dropped. Jay, are you still hearing me?
We lost you. I think we lost you for a bit just before this, but now we can hear you again.
Okay, it might
But
go
when
out.
you started talking about the attenuator, you went silent for, I think.
Okay, am I audible now? Hello, Jay, am I audible now?
I think the voice is a little patchy.
What's going on today?
I think it's fine now.
Oh, it has somehow dropped from my hotspot and reconnected. Just give me 2 minutes. I'm going to reconnect again. Okay, can you hear me, Jay?
Yeah, but I think your connection is still a little unstable.
It's terrible today. What's going on? Okay, let's try for another 5 minutes. If it is very bad, we'll stop here and then pick up tomorrow. Anyway, we're coming close to an hour and a half. So
I think it becomes bad for.
yeah, I just your voice just broke off after it becomes bad. I don't know.
No, actually, yeah. I muted myself. I thought you were just continuing. So
Okay.
yeah,
Okay.
it seems fine now. Yeah.
Okay, all right. So let's quickly go through. So this calculator, basically you specify the attenuation value, which is basically the ratio of output power to input power in dB units. And then it gives you what values of R1 and R2 is. And it's important to specify the characteristic impedance of system, because remember, we just calculated that total ZL should be equal to 50 ohms because we are in a 50 ohm system. So this is always true by default, but it's important to specify this for the calculation. But you could have a different system. Okay, so you see that for a 3 dB attenuator, you get something like 8.5 ohms for R1 and 140 ohms for R2. And that R1 plus R2 is not really the number which has to be equal to 50 ohms as we just calculated, but it's this 141 ohms in parallel with the 8 plus 50 ohms, which now will give you something close to 42 ohms, which then added with R1 will give you 50 ohms. Okay, so let's enter these numbers in here. So 8.54, that 141.93. Okay, and we'll first look at the transmission and reflection. So let's add all of the 4-port networks. It's 1 and it's 2. Now this is a completely frequency independent circuit, so it really doesn't matter what frequency you choose, but let's just say something like just C flat and here. So the transmission you see is close to 3 dB, right? Minus 2.98. It doesn't matter on the frequency, and you get some very small return loss. So minus 76 dB is basically like 10 to the power minus 7 in power. So it's essentially 0 in the linear units. So if we had looked at this in non-dB units, maybe let's just do that. Let's get out this dB. Okay, so you see this is because this is the this is no longer the power. Remember, this is the transmission coefficient, not the power, but square of that would be, and that will give you 0.5 because 0.7 square is 0.49 or so. Okay, so that's half. And then this number is basically close to 0, and you see S21 and S12 are the same, and S11 and S22 are also the same as expected. Okay, so this works like a 3 dB attenuator. We can now look at the impedance matrix elements as well. So let's make another graph and now put in the add measurement. Now we can go to the impedance quantity. So again, in port parameters, let's choose Z. Let's choose Z11. Magnitude is fine. Anyway, everything is real. So magnitude or real will be the same. We add that, and then we add Z21. And Z12. Z22. Okay, so the Z21 is the pink one and Z12 is the brown one, so they are same, and it's 141.93, which is what we had said, that the transfer one, this is equal to this parallel value, and we had entered 141.93, so that's come out exactly that. And this is the sum of the two resistors. So it's 141.93 plus 8.54, which is about 150 something, right? So this is matching. So the matrix element definition is as is. Now let's see what Z in is. So remember, Z in is a quantity which is only connected to one port. So in fact, I'm slightly unsure about what result we will get. And this is why I was pointing out this point regarding how the other inputs are terminated is very important. So if we now go to linear and then we go to Z in, and let's look at Z1. Anyway, Z1 and Z2 are completely symmetrical, so there will be no difference. So let's see what this looks like. And it's 50 ohms. Okay. And this is because it is considering for this measurement, it is terminating all the other inputs with a load. Okay. So this again is a boundary condition. There are typically three types you can do. You can have the ports open. You can have the ports short circuited, which actually means connecting this point to ground like this, so that you have a current, maximum current flowing through it, not through 50 ohms, or you can have it connected to a 50 ohm circuit. That's called a load termination. Okay, so the convention must be that if you're measuring the quantity Z in, then all the other ports must be terminated with the port impedance, which is the 50, which in this case is 50 ohms, and that's why you're getting 50 ohms. So we can see this, that if I now disconnect this terminal here, of course all the other things will also get messed up, but the Z in is okay, this is, I guess, no problem. Let me just disable. Yeah. Now this is measuring 140.7, which is essentially the sum of, sorry, not 140, what was this? 150.47, which is essentially the sum of these two. And that makes sense because now with this thing open circuited, you have just these two resistors in series, and that is what would be the input impedance. Okay, so I hope this is now somewhat clear that what Z in is and what Z11 is. Now, if it was only a single port, there is no other quantity. Those two are exactly the same. There is no other port to terminate or provide any boundary condition. So then it's just the total impedance between that port and ground when in the case of a single port. Okay, so yeah. Okay, great. So all this is clear. I'll just now make a few more sort of useful points when concerning attenuators, just to sort of keep in mind, and that we can see just by looking at the values. Just note how R1 and R2 change as I increase the attenuation, right? So I'm at 3 dB, let's go to 10 dB, okay? So now R1 is 25 ohms, R2 is 35 ohms, okay? And you can, play around with this in Microwave Office and convince yourself that it gives you the correct reflection coefficient. Just one point is that, the return loss should ideally be 0, which in dB units would be minus infinity, right? Now, what basically this calculator is trying to say is that the exact calculation you will do for getting a gamma 0, the R1 and R2, you probably have to define to some arbitrary large number of decimal places. And that is something you can never control anyway in a realistic circuit. In fact, 0.975 and 136 is also really at some level meaningless. You can probably really just do this and then you have to calculate what you get. So it's close enough for most applications. And then the return loss is the one which looks like it's dramatically changing, but minus 60 dB is still 10 to the power minus 6. It's an extremely small number. Okay, this is one practical point. But now you notice that the sum of R1 and R2 is about 60 ohms, whereas earlier it was something like 150 ohms. Okay, and then let's go to 20 dB. Now R1 plus R2 is almost close to 50 ohms. Okay, if I go to even larger, let's say 40 dB, then it's again close to 50 ohms. If I go to 80 dB, it's again close to 50 ohms, right? See 49.99 and 0.01. Okay. Now, can someone explain this trend to me? Joydeep?
Yeah. So Okay. So,
Let me show you another thing. If I change the convention of this thing from a 50 ohm system to say some arbitrary value, let's say 126 ohms, and do this, look at this value here, R1 and R2 is 128 ohms. If I go to 40 dB, it looks closer to 126 ohms. If I go to even higher, second, even closer to 126 ohms. Okay, so it's not a fluke that it is adding up to 50 ohms is what I wanted to just say, that it's actually adding up to Z naught. Now, can you tell me?
yeah, so maybe in this case, so R1 plus R2 is reaching near the impedance of the coax, let's say the port 1. Then all the power is going to the ground through R2.
Power is not going to ground.
No signal is
so that
transmitting
is
out
not.
to port 2, rather.
No, but port 2, the signal is going,
No.
man. By the way, you should be careful.
Okay.
I mean, I guess
Yeah, so,
you
yeah,
come from the DC side, but you are also doing RF measurements. That sentence is just wrong. The power is not going to ground. Okay, there's no. You're like thinking in terms of current and not power. Power is only being dissipated in the resistors. It's not going to ground anywhere. But I think you are getting close to. You're just not phrasing it correctly. Why
so,
does R1
yes.
and R2 become closer to 50 ohms?
It is maybe reflecting the whole signal. R1 plus R2 combined, it is close to.
No, not reflection. Okay. Srijita?
This R1 plus R2 is equal to Z11 or Z22. So,
Yes.
If the attenuation is higher, so it must mean that there is a larger voltage drop across R2. No.
No. Jay?
No.
I mean, I was going to say something similar to what Joydeep said. It seems like this R1 plus R2 is this arm of this circuit is more and more matched to the input circuit, and that restricts that. So most of the signal just uses that path, and very less of it is transmitted across to the second port.
Okay, that is a much better description of what I think Joydeep wanted to say. I
mean, that's
okay.
how I was imagining.
Let me. No. So that is, that is basically correct. But the way I like to think about it is like this. If the attenuation is very high, which means very little power is actually coming out here on this port. Okay. Which means that if the boundary condition here was a short circuit or a load or an open circuit, the amount of power which will come back in case it's not 50 ohms, because remember that if it is matched, then this is designed to not send any power back. But if it is not matched, and let's say it is left open or left short circuited, then the amount of power which is coming back shouldn't really make it back here. Why? Because to go from here to here, it already has now become 0.01, right? Because it's attenuated by a factor of 100. And then even if all of that power reflects, when it comes back here, it is now 0.01 into 0.01. So it's 10 to the power minus 4. It's almost no power is coming back. So if I measure the reflection coefficient here with different boundary conditions on the other side, it will actually look very similar to 0, because that is anyway what you want. So when the attenuation becomes very much larger and larger, the role of R1 and the 50 ohm which is connected here becomes less and less from the point of view of matching to 50 ohms. Okay. What is the practical sort of rule of thumb kind of thing you learn from this is that if I take an attenuator and I just measure the resistance across its center pin and ground, for larger attenuators it will always be 50 ohms or very close to 50 ohms, because it doesn't require this extra, this part of the circuit to give you that 50 ohm matching thing, because the power absorption is. But did you lose me at any point?
Yes, we lost you when you said something about when you were starting to speak about the practical aspect.
Oh, okay. All right.
Then you went completely blank.
Yeah, my laptop lost connectivity. I don't know what's going on. Can you still hear me?
Yes, yes.
And what the hell is going on? Hello?
Hello. Yeah.
Wait. Did you even hear anything at all?
You were mute all this time, so we thought you were doing something else.
Okay. Oh my God, what a comedy. Sorry, just to say this again. All right. So here, I mean, again, I guess the point I was making, the practical point I was making is that if you have a attenuator sitting in the lab and you don't have a quick way of knowing what it is, you can just measure the resistance between the ground and the thing. And if it is closer to 50 ohms, then it's most likely that it's a 20 dB attenuator. And the point is that typically the attenuator values one has are 20 dB, 10 dB, and 3 dB, and sometimes maybe 6 dB. Okay, so only the 20 dB attenuator will have a resistance between these two terminals, which is and it will be close to 50 ohms. So this one and ground, or this one and ground, it will be close to 50 ohms. And the reason is that because there is such little transmission, the impedance matching on 250 ohms does not rely on the resistor on the other side. It just relies on R1 and R2 mostly. And then R1 plus the other one. You see, you can also see it from the fact that as attenuator becomes larger, sorry, just checking again, still audible, right?
Yes, almost.
Okay, so as the attenuation becomes large, R2 becomes small, and then R1 sort of becomes somewhat large. But then as this becomes small, R1 plus 50 ohms is going to be a much larger resistor in parallel with R2. So that means the effective resistance between these two terminals will just be R2. So it then makes sense that R1 plus R2 must already be close to 50 ohms to give you good reflection, sort of minimal reflection on that. Okay. All right. So we'll stop there, and we'll continue tomorrow at 5 again. And we'll now look at the scattering matrix related ideas, which is very closely connected. And of course, we have already discussed this in many other ways. And we'll finish up. So are there any questions? Jay, still audible?
Yes, audible.
Okay, all right. So let's stop there, and we will continue tomorrow at 5 o'clock. Okay, bye-bye.
Okay. Bye.